Hey Trey, this is Todd Ensign from the NASA facility, and we're going to do a little overview of RockSim or Open Rocket, really, and where to get the parts, maybe some CAD work as well. And we're going to answer some questions that you and your team have come across, but I think it'll be beneficial for all the teams that we're working with and mentoring. So I want to begin by sharing some web pages that I've been looking at that I think are going to be helpful for the team. So always begin. Can you see the page?
Yeah.
Okay, so always begin all of your work by writing down the requirements. So this is this year's rules for 2024. And if you scroll down, what you'll see pretty quickly after safety and how to form teams is this part right here on rocket requirements. And so these are things that we would definitely, kind of highlight here. So we can't weigh more than 650 grams. If you're pushing that, then you're also pushing the limits of an F engine to get up to 800 feet.
Okay.
But this is really key here. This will affect your design. Your rocket must be no less than 650 millimeters from the lowest to highest points. Okay. This is the next part that's really key that affects this year's challenge, and that's different each year. You have to use two body tubes with different diameters in their exterior structure. The upper must be no greater than 2.25 or 57, and the lower one must be no less than 2.5 or 63. It just so happens that these two dimensions line up very nicely with standard parts that are available from any rocket supply company. The smaller or upper section, which we will call our payload bay in the future, is essentially a BT-70. That doesn't even refer to the diameter or anything. It's a commercially accepted name for a rocket that's 56 millimeters in diameter, a body tube. And the no less than 2.5 or 63 lines up very nicely with the 65 millimeter diameter BT-80 body tube. So from now on, we're going to refer to BT-70 as our smaller diameter body tube, which will meet the requirements, and a BT-80 as the one for our booster, which will be the bottom part of our rocket. Each body tube must be no less than 6 inches. So that's another thing that's going to affect us. You can't have a tiny little payload section. So you have to have, at least 12 inches there. But if you have a 25-inch rocket, then that shouldn't be an issue. Just to keep that in mind. When it comes back down, all parts must come together. Now, this is one of the areas where they change it each year. Sometimes they come down as two separate pieces, which it would necessitate two parachutes. This year we can have one parachute, and our booster and payload are connected together by a shock cord. There's some other details about what you're going to use here, and decorations and stuff. And you have to use an F or lower class engine. So when you cross into G's, some G engines are level 1 certificate required, and so you have to basically stick with Fs, which is easy to do. In fact, more likely you're going to have a problem going too high, and you have to slow it down. You do have to use commercially available rockets engines, which is super easy because that's the ones that will be available for us to just purchase. So with the payload area, we're going to carry 1 egg. We've had as many as 3 eggs in the past. And so I usually, it says 55 to 61 grams. I usually just stick with 60. And I figure if I end up with a lighter egg, I'm going to pack it with clay anyhow. So I always have 60. So shoot for 60 and pack some clay with you. So if you need to boost it up, that gives you that consistent weight load in your payload area.
Okay.
And as far as diameter, that's, not, you don't have a whole lot of control over that. Duration scoring. So this is all the pretty standard stuff, but essentially you're trying to shoot up to 800 feet. So this will tell us in here where our altitude is, right? Let's see. Stopwatches. Flight duration. 43 to 46 seconds. So that's going to be key. And again, this will come in when we look at the simulations. This will come into play. Here's altitude scoring down below, and I think we're shooting for 820 feet. Is that right? qualification 820. So we'll probably jump back to this document in a little bit to talk about the rocket, but suffice to say we need BT-70, BT-80s, and F engines. So I'm going to jump.
What happens if you get under 820?
You get a point added to your score for every foot you are above or below 820.
Okay.
So I am not advocating this is the only place to buy parts, but I will tell you that Apogee Rockets does a fantastic job of detailing the exact dimensions of every product they sell. This is very helpful for simulation purposes. So here is a 56 millimeter TARC foam nose cone. You are not going to gain, I will tell you, according to laws of physics, you're not going to actually soften the blow or anything by using a foam nose cone. Than if you used, for example, a plastic polyethylene nose cone that would sort of stab into the earth. That actually disseminates force better than a foam one. But practically speaking, these foam nose cones are pretty nice because they have an 18 millimeter hole already in them that you can stick a piece of tubing in and put your altimeter inside of it. So it's convenient for nothing else. And they're really cheap based on, other options. But we can also 3D print our nose cone. So here's a commercial nose cone, a PNC 56A BT-70. I'm starting here on purpose because I want to show you that this is the first part of your rocket you're going to begin with when you build it. And if you want to start making things and customizing them in CAD, I will go over that. But let's start with the KISS principle. You know what that is, right? Keep it super simple.
Yeah.
Okay. And I had some tips on the rocket that you sent me earlier to look at that I think we could simplify in a few ways and just make it so that when it does land, you can reuse it right away again. So some of the designs, like your fins sticking out below your body tube, they're gonna tend to get broken off.
Okay.
But we're going to start with this thing. It's a PNC 56A. It's a BT-70 nose cone. Okay. And you can see right here, I have and we're going to go all metric today for the most part. Once in a while, I'll jump into inches, but practically speaking, for all of the design work, we're going to stay in metric. And I standardize generally on millimeters because that's what I use in the CAD programs as well. But so these are the dimensions we're going to look at. So PNC 56A. So I'm going to jump now. I'm going to have to do a different share, a new share. I'm going to jump over to Open Rocket. Let me know if you can see that.
Yep.
Great. So when you launch Open Rocket, we're going to begin up here. You can see the assembly components. A lot of it's grayed out. The software is intuitive and intelligent. And so it's only telling you, well, you really can't begin with an inner tube or a coupler if you don't have any tubes.
Right.
But I'm gonna advise you strongly to begin every rocket with a nose cone. Okay. And it pulls up by default a whole list of commercially available nose cones. Well, that's pretty easy. And so I know I'm looking for the PNC BT-70 nose cone. So PNC. And it was the 56. Okay, and that's a black. Okay, PNC 50. Is that the one I wanted? Black bowling PNC. Okay, so it's now we can look at the diameters and see if this is the one we want. For sure. That does not look like it, does it? Because it says
I don't see that. I don't see the.
Are you not seeing this window?
Uh-uh.
Oh, it pops up in a whole new window. All right. Well, thanks for letting me know that. Here's what I'm going to do. I'm going to share my whole screen. And hopefully it doesn't share our pictures of ourselves on top of our. So let me try again. Let me share entire screen. Desktop.
There you go.
So let me start over. Let me close that. Okay. So when I begin, I'm going to select a nose cone. So I'll just go in here and just delete this part out for a second. So we begin with, we're only going to have one stage in this rocket. So don't worry about the stage button. And on this one stage, we're going to begin with a nose cone. And what I'm looking for is I can filter by typing 56 in here. And here's a LOC 2.56. And so we are looking for one that is a BT70 size. The OPN. I'm not sure this is the right size. 2.5. I think this is the one. Okay, and I can confirm this. I'm sharing my whole screen, so I can jump back real quick to the page I was looking at. So we are looking for one that should be 10.5 inches long. The outer diameter should be 56 millimeters. And so this one is 66. So I should be able to find the appropriate one in here. It's PNC 56. I think this is the one. It says black. It still looks, some of these measurements look wrong to me down here. The shoulder, the length. Where's the diameter? The aft outer diameter should be 56 millimeters. That's 34. So I can sort by anything, by the way, which is kind of cool. So let's just sort by the aft diameter for a second and find things that are the 56. So these should be the nose cones that we're looking at. The PNC, ogive. This looks like the right one for us. And this is 57 here. So these are some of the ones that I think are the ones that we would buy. But PNC 2.14, PNC. And so I can choose which one I want. So this one now, let's look at the measurements. It's 241 millimeters in length, and it has a 57 millimeter base diameter. And so 56, yeah, so this is basically the nose cone we were looking at, right? And it's 266 millimeters long, 200 and so I can tweak this a little bit. The one that we were looking at in the store was 267 millimeters long. But the base diameter is right. The wall thickness. Now this is, I was looking at this nose cone earlier, and it says the wall thickness is 3 millimeters thick. I do not believe remotely it's 3 millimeters thick. And so I'm gonna go in here and look at the weight. It says 50 grams, right? And it's a styrene nose cone. So polypropylene, I think it should be say polystyrene, which is one of the options. So it's polystyrene. So it's possible I just chose the wrong nose cone, but I can configure it. And here, this is an important lesson to learn, which is what I'm doing right now, which is probably something you didn't see earlier, is I'm going to ensure that when I add this nose cone to my rocket, it does match in weight and dimensions what I want. So if I go and make my own custom 3D designed one, I will do the same thing. I'll make sure that my simulation is matching what I designed. So the wall thickness is definitely not 3. I mean, I'd be surprised if it's even 1 millimeter thick. But let's see how our mass is now. 65 grams, and it says it's going to be 50 grams. So we're still gonna drop a little bit. We're on 34 grams already. Okay, so 41, and there's another way to do this, which is there's a mass override. 45 grams. So if it was 1.5 millimeter wall thickness, then it would weigh in at the exact weight that it's supposed to. Right now we're unfinished. We did not paint it. Okay. And I believe this is what we call an ogive nose cone. That's the shape of it. And I think the length is correct now. It was 266.7, so 267 millimeters. The shoulder, so your nose cone that you put in there that you were designing didn't have a shoulder, and you need one. Otherwise, it can't slide into the body tube. So the diameter of the shoulder should be the interior diameter of the body tube. So what does that mean? Well, if we go to Apogee Rockets and we look at a BT-70 body tube, the inner diameter is 55.4. So the inner diameter is, this is 54. So that means this is smaller than the inner diameter, and that's fine. That's what they're saying the custom measurement is. And we could also look at the actual rocket nose cone that we're looking at, the shoulder length, the outer diameter. I'm not sure it shows me shoulder diameter, but it's going to slide into a BT-70 body tube. So this is weird. It says 0 thickness in the walls, and I'm going to say it's at least, we said 1.5 the other one.
Yeah.
Okay. So now we've gained some mass here. I'm going to say it's all 1 millimeter. General 44. So I think we're getting pretty close to what it is. Okay, so it says 54 grams. So we're there. So this nose cone works. And we are hoping that this is the PNC 56A BT-70 nose cone. That's the one that we're hoping that we're buying. And we're going to use it here. So I'm going to go ahead and rename the part. And we have it. So if you see, we now have the beginnings of our rocket. Over here in the list of parts, I'm going to click on the nose cone because I'm going to click on what I want to build off of. So if I want to add a tube or a fin, I first click on the body tube I want to put that fin on. Okay, otherwise it can create a part that's not attached to where you think it is. So attaching to that, I now have options for, I can't do fins and stuff yet, but I can do a body tube. And in here, I should be able to do, Estes makes the basic BT-70 body tube. It should be 18 inches long. Let's see, Estes BT-70. So this is the part right here you want. I think this is the part you used in your rocket as well. Okay. It's showing as fantastically short for some reason, but we want to make sure this is at least 6 inches long, right? Which that's what the directions say, which means
So you said it can't be less than
no,
25?
not less than 100 millimeters. Yeah, so it can't be less than 150 millimeters long. So you can see it forming down here, right? So now we're getting a payload bay, but let's just start by making it quite a bit longer.
But so for the whole length of the rocket, it can't be 20, or it can't be less than 25.
The whole rocket length, yeah. But I'm just gauging this right now. I'm just gonna make up a number right here, and we can play with this later. But let's just make this 250 millimeters. It said it had to be at least 160, so that's cool. So it says right here that it's 55 millimeters outer, 0.533. Again, these are like less than a millimeter thick walls. They're paper. They're craft, spiral craft paper. Okay, I'm unfinished right now. It's telling me that it thinks it's going to weigh 20.9 grams. That seems consistent with what I would expect. You know, in terms of, there's a nose, there's a body tube. The entire thing weighs 36 grams, and I just cut it down quite a bit because normally this comes into 18-inch length. So I'm going to stick with that and say, okay. So now we're starting to look a little bit more like a rocket. Okay, the next piece is going to be a transition. And the transition piece is going to go from BT-70 to BT-80. Now it's a trick to try and begin with commercial parts if you can. Okay, so here's a 70 to 80 right here. And if I use that, what's it made out of? Conical. It's made out of balsa wood. It'll just give me some measurements. It'll be helpful for me. I could find one that is a 70 to 80 made out of something besides balsa wood, I guess. But it's just gonna be it's gonna be useful for me to get this going and started. So we'll start with this as a example. Okay, so it's showing me this. Now, what I'm gonna do in here, I'm gonna make this out of 3D. I'm gonna print this.
Okay.
So my material, and I've done some testing as well, the closest density I found in the software to PLA and ABS plastic is actually polycarbonate lexan. So when I do 3D parts, that's what I usually use as my simulation density. I didn't show you this, but there's always an override. You can always override the mass. If you got the dimensions all right, but it's the mass coming up wrong. Okay. So this shows that it's going to slide into the upper payload bay here. And it shows you that that shoulder, the fore shoulder, upper shoulder, is 31.8 millimeters. In case you want to convert that to American, that's 1.5 inches. Okay. And the bottom one, okay, and this is the one that's going to slide into our booster. It says it's the same, right? And 1.62. Yeah, so I might actually make that 2 inches, which back in millimeters is 50. Okay. So that's cool. 50 there. And this one we're going to glue in. So it won't really matter, but we can make this. It's not as critical a part that I'm going to glue in that it have enough to slide together and be stable as one that's going to be sliding apart. So I'll make that lower, the aft shoulder, a little bit bigger, longer. In general, okay, it has a certain length, it has a certain diameter. Okay, now here's the wall thickness. They're saying it's balsa, so it's totally full. We're going to say no, the wall thickness, and this is my advice on parts. When you're 3D printing, 2 millimeters is a good 3D printed thickness for nose cones and certain parts of the rocket-like transitions. Technically, I'll show you how we can make this transition in a way where the bottom is thicker, because you will blow out the bottom with the forces of the ejection. I've broken rockets at the bulkhead. We're going to build the bulkhead into this, but you'll see how that works.
So somebody had a question. They were questioning my rocket, or they were asking about it if it would have enough power to blow out the payload tube.
Oh yeah, plenty. It's going to overblow. In fact, it's going to blow so hard that if you don't have a long shock cord and maybe some elastic in there too, you chance ripping the rocket apart, or what's called zippering. You know, your shock cord could rip right through your body tube. But you'll have plenty of force. I wouldn't worry about that.
Okay.
So it's 2 millimeters thick. It's saying it's about 308 grams. That doesn't sound right. I think that's because it hasn't figured out that it's hollow yet. 308 grams sounds like a lot to me. Are we overriding the mass? No, we're not. Yeah, I can't really believe it's 300.
Is it because it's 50 millimeters long?
So you think that's too long?
I wasn't.
Yeah, I don't know.
Well, no. Maybe, I don't know.
Let's leave it for now, but that sounds too heavy for me. And I'm gonna call this my 3D printed transition. And I didn't even add the bulkhead yet, so the 308 grams isn't even counting the bulkhead. But we'll see. Okay, so we have that part. Now the bulkhead will be printed into it.
Okay.
I don't want to jump too far ahead, but let me just show you something that I think will be interesting. And that is, here is my on shape parts. And here is a part that I built that I can share with folks if you want to look at it. But this is a 70 to 80 transition I made for another class that I was teaching. Okay. And so what I can do with this, if you look, the bottom's solid.
Okay.
The top, though, is hollow.
Shelled out.
Yeah. And so what I did, I made this through what's called a revolve. And by doing a revolve, it allows me to make a thicker bottom bulkhead. So if it was only 2 millimeters thick, I think you'd crack it. I would say at least 3 millimeters thick for that. You can go even thicker if you want, but I'll show you how we do that.
I don't know. I'm not sure on how to make the nose cone either in on shape. I've used it before, but I'm
Yeah, I'm also going to use a revolve for that. So I'll show you how to do that. Okay, so now we have a transition. It's already highlighted, but if it wasn't, I'd highlight that, and then I'm going to add body tube. And I'm going to do a BT80. So here's a BT80 from Estes. And I'm not sure what the difference any of these are, to be honest. This is a fat boy. This is a 8-inch BT80. Here's a slotted one. So it has slots for the fins, but I'm just going to buy a standard BT80 body tube for now. Okay. And for whatever I'm selecting, it seems to be coming out short. But most of these are a lot longer. Like I said, their standard is like 18 inches. Now, what I'm able to see at this point, I can see the rocket length over here, 938 millimeters already. The requirement for the rocket was that it must be no less than 650 millimeters. So I'm well past that, right?
Right.
No problem. And that looks kind of balanced to me. I don't know. I'm just kind of making that number. Well, let's say 350. That look okay?
Yeah, that looks good.
Okay. Just checking the mass here, 32 grams sounds right. So I still have a question about that coupler, but otherwise this sounds fine to me. It's unfinished, it's craft paper, perfect. Now click on this body tube, and we're gonna say inner tube. And this is another thing that I wanted you to correct on yours, but I'm not even gonna choose from a part here. So I'm gonna make my own. I'm gonna 3D print an engine tube. Okay, so again, I'm gonna use polycarbonate as my material relative to the bottom of the component. I would suggest you always choose one relative position. Otherwise, you're sliding parts around and it gets weird. You slide the slider and they start moving the opposite direction because it's relative to the nose or relative to the bottom. So if you're always relative to the bottom, then it's easier for you to keep track of what's going on. Now, I know what this part has to be. I'm making a engine tube that is intentionally meant for an F engine. So I'm going to go ahead and go back to Onshape.
It's 25. It's 29 millimeters, isn't it?
Right. So here I'm going to show you an engine tube. So here's my engine tube. Okay, and what's important to know about this engine tube is the diameters, right? So I have an inner diameter of slightly more than 29. So if I go to my sketch, let's see, what did I do here? So you can see my measurements now, right?
Okay.
29.1 I gave it. I gave me a little extra room. There's like a sticker on the outside of your engine and stuff. And if you're exactly 29, you might have trouble getting that engine in there. Okay. And what I want to do is I want to make the thickness of the walls. I told you earlier, 2 millimeters for most of my things. And when I'm doing structural parts that are going to get forces, I make them 3 millimeters often. This is just my advice. You can do whatever you want and experiment. But 29 plus 2 millimeters on this side and 2 millimeters on this side comes out to 33, basically. Okay. Right? So yep. I know this, and also, how long is this this puppy?
It depends. The different motors are different lengths.
Right, but so how long should I make my my engine tube? And I can look in here, I made mine 100 millimeters long, okay? I'm showing these dimensions because as we go into Open Rocket, we're gonna say the outer diameter is 33 millimeters. The inner diameter is 29.1 millimeters. It calculates my wall thickness for me right there. See that? My length is 100 millimeters. My material is polyethylene, okay? Now, I want it to slide out of my engine, my rocket. Another thing that I would recommend for you, again, based on my prior experience, is you want this thing sticking out of your body tube by a little bit. Like I usually say like a half inch.
Okay.
Just so if it sticks out approximately, 12.7 millimeters or something like that, that's pretty cool. That'd be my advice to you. I think I actually made my part a little more sophisticated. We added a little tab on here in the second extrude. And that second extrude was another 10 millimeters. But what that allows us is it's a thinner cutback version where we glue on a retainer ring. And I can probably show you that retainer ring in Apogee rockets in a bit. But anyway, so that means it's sticking out 12.7 millimeters. So it's actually my retainer ring is going to cover that. So I want to make this, I'm actually going to make my length 110. Okay, it sticks out a half inch. That's good. So I have this. It's saying 25 grams. That still seems a little heavy, but that's probably okay. We can validate all this stuff using a balance once we printed the parts out. Now, what's going to hold that engine tube in place? I click. Oh, I should have named it. This is my 29 millimeter engine tube. And that's important because when we go to choose what tube we put an engine in, we have to choose that tube. Okay, so I click on that. Now I look and I should have an option for centering rings. Okay, I'm gonna cancel the manufactured ones and make my own. The button that says automatically calculate is your best friend ever. It's wonderful. Okay, so relative to the bottom of the parent, I'm gonna slide this ring up. I'm gonna put the one right in the very bottom of my rocket, right there on the bottom. I can get it. Okay. No, wrong way. Good. It's not made out of cardboard. It's going to be one that I 3D print. So I'm going to go with polycarb. And it is going to be 3 millimeters thick. And
So what does the centering ring do?
well, actually, it looks like my centering is in the wrong place. So I made a mistake. This is kind of cool. You just watch me make a goof. It's putting my centering ring inside my engine tube.
Yeah,
and I
that's
don't
what I was
actually want
confused
that.
about. I thought it's like a little ring that goes around your
Yeah, so I should have clicked body tube here, and that's actually I should rename that my booster. Okay, so I click on the booster, and then I add my centering ring. And then what I do, you can see it now, it's filling the it's going all to the insides of there, but it's going to also do a ring in the middle that it's automatically calculated for the engine tube. So I'll make this 3 millimeters thick. Okay, the outer automatically calculate the outer diameter as the inner diameter of the body tube. These are exact measurements now. Exactly what the inside is, you'll do the exact measurement for things that are press fit. These are tight fit things. I want my engine to slide in and out of the engine tube, but I want my other parts to all fit really tight.
what holds the engine inside the engine tube?
A retainer ring, and I'll show you that. There's a lip on the engine itself that keeps it. That's a thrust ring built in, keeps it from going through the rocket. And when it ejects, there's a retainer ring that'll keep it on, or duct tape. Duct tape's fine, by the way. Works great.
Have you used duct tape before?
Many times. Okay, so this this shows its relative position is 0, which is exactly what I wanted. Okay, and hit OK. Now I'm going to cheat. I'm going to go over here. I'm going to click on that part, right click on it. I'm going to say duplicate that part. And I'm going to call this one up here my top. Come on. Top centering ring, and I'm going to slide it up. Now, I don't usually put it on the very, very top here, but somewhere in this general area. You could put it in the very top of that tube, but this is kind of cool because it gives you a little bit of extra space for more glue.
Okay.
It does limit the size of your fin tabs, though. And so you can actually drive the length of this by where you want to put your fin tabs. Now, this one says it's only 8 grams. That sounds right to me. The other ones say. Oh, 8. Okay, so the other one's good. This is my bottom. So now I have 2 centering rings, so now I can hold my engine tube in place. I can come back to your question about how to hold it in. But there's a part we'll glue on, and we glue it right onto this little lip that I intentionally made on my engine tube.
Can you add threads to that little lip and then make a piece that threads on there?
You could, but for a few dollars, I buy that piece.
Okay, because I have this little, it's a little Model B rocket in it, and it's like that. It has like a little plastic thing.
Okay, we're gonna go there. We'll go ahead. I'd like to. It annoys me when I'm listening to a talk and we don't answer the questions. So let me just duplicate this tab. So we're still in their shopping area. I go to shop. I go to building supplies. And we're looking for a retaining ring, centering rings, bulkhead. There's a bulkhead that stops the thrust of the ejection charge. Rail guide buttons. Payload bay, shot cord. I want a retaining ring. I might be in our miscellaneous hardware. I'll just search for it because I don't really know where he's got it. Right here. See this?
Yep,
It's
that's it.
24 millimeter. I want the 29 millimeter version of this. So
Okay.
that glues right on, and it has the threads there, and that part threads right onto it. Yes, you can 3D print it, but part of what I'm trying to do is show how with only a few clicks I can 3D print the parts that I need. And for $10, you get 2, so it's $5. So it's really worth it. I want to be shows the similar products, so I can show you. There's all different kinds of ways of holding your engine in. But here's 24, 24, 24. I wonder if he has the 29. Compare some other 24 millimeter things. Well, at least here they are, down the bottom down here. Here's 29. That's the one that I want. So I'd recommend you buy this. And it's meant to glue onto a paper tube, which you saw has less than 1 millimeter thickness walls. So by designing my engine tube with that little thinner end there to it, that gives me the place to glue that right on there. Okay. And it works great. It's really works fantastic. All right, so now we're not done with building our rocket because it needs to have some fins. So I click on the booster because that's where the fins are going to go. I want to say trapezoidal fins. Okay, so these look kind of like the fins you had, but from real world experience, I'll tell you that if they stick out below your rocket, they're going to crack off. Okay. So I can play with these different dimensions here to get my fin in a better place. So first, the root cord is the bottom part touching the rocket body. So by sliding that up, I can make it a bigger fin. I can change its height, which is how far it is from the body tube with this. Okay, so that's kind of a cool looking fin so far. I'm not objecting to that. Okay, the sweep length is the front angle. That looks kind of cool. No problems. I got no problems with that. You can do it. I don't know. Do you like this better? Or do you like this better?
I like that better.
This one?
Yeah.
So we're going to say that. Now, we're going to have 4 fins. because my thought is that's going to make you more stable. It's also going to give you some drag. If we don't go high enough, you can always drop a fin. It'll cut back. You can't
Okay.
really go more than 4 though, or you won't get on the launch rail. If you have 5 or 6 fins, you can do that, but then you're going to have like a long tail guy that sticks out past the fins. It's going to be really awkward. So don't do that. Now, what I want to do next is define some more parts about this. It's not made of cardboard. You had yours as cardboard. So I'm going to make this out of wood. I actually prefer wood. And I have some birch and I have some other sort like wood that I have. I have balsa as well. But the birch is really strong. I have it in a variety of thicknesses and I can laser cut it right out. So I know you have access to a laser cutter, but it is fantastically cool to do that. If you guys design your parts and you want a laser cut on our cutter, you're welcome to do that. Also, our CBI will be happy to cut your fins out for you.
Okay.
Or you can go over to RCBI and they'll do it. But like I said, I'm going to make mine out of birch, which is dense. It's kind of heavy. Okay. It's unfinished right now. And I'm not sure how thick it is exactly. I want to say it's probably at least, I don't think it's 1/4 inch, but it might be 1/8 inch. So 1/8 inch would be what, 1.25 is 1/4, right? So 0.1 should be 1/8 inch.
So what do you think 3D printed fins would do good?
No. Yes, you can do that, but it adds a lot of weight and they're really hard to glue in. They're if you can super glue, if you can super glue 2 3D printed parts together with super glue, it works great. But when you try to start gluing 3D parts to paper and wood and stuff, it gets weird. I prefer wood fins. You can definitely 3D print fins though, and I've done it before. We've done really cool airfoiled fins and stuff. I've done through the wall fins. But for simplicity, let's just say we're going to do some wooden fins.
Okay.
I believe deeply that you should do through the wall fin design. Okay. A through the wall fin is going to extend all the way down to your engine tube and it's going to press against also your centering rings. It gives you all this contact in here. And if you put some Gorilla Glue, which expands like that foam, when you glue it in there, it's going to be locked in there like it'll never break off ever. Like your entire rocket will shred and this thing will still be perfectly fine. So I'm going to use the automatic button to calculate these, and you see what it just did? It automatically extended them down to the engine tube and from ring to ring. That is awesome. So that's what I want. It's saying they're 48 grams. That's perfect. I love it. It looks good to me. And I'm going to call these, they were birch, right?
Yeah. So how do those work, really? So it goes through your tube, and then
I'm going to show you.
okay.
We're going back to Apogee Rockets. We're going to shop for another part. Okay, this time we're going to do slotted body tubes. So you can buy your body tube slotted. So you see this is a BT55, 60, 70, here's an 80. Okay, that already has the slots in it. Now this is designed for 3 fins rockets. Okay, and but that's a BT80 body tube and there's already the cut in it. And then what'll happen is if you look at Rock Sim here, I'm gonna do a quick save and call this. Okay, if I look at the back, can you see how that tab extends through the body and touches the engine tube?
We have to create slots in the centering ring to fit
Nope, nope, nope. It just glues against them.
Okay.
More surface for the fin to glue to. Okay, now this rocket is kind of viable. It has a center of gravity and a center of pressure. So that's pretty cool. You remember those from our previous talk. If I want to add that ring in the bottom, that little retainer ring, it does weigh something. It weighs 13 grams. So what I can do is I can click on the actual engine tube. I can drag these down too if I feel like it, just to make it makes more sense in my head. The fins are up here or whatever. It doesn't, but I can click on that and I can add a mass component. And I can call this the retainer. And it was 13 grams, right?
Yeah, I think it was 13.3, but
From the top, I'm going to say from the bottom. So we'll put a little glue on there. So we'll call it 14 grams.
okay.
And what I'm going to do is I'm going to slide that thing down to the it's literally sitting right there. Okay. That's my retainer ring. And I can also, it's the way it looks on here, I can change its appearance if I want, default colors and stuff like this.
Do you like to add colors eventually?
If I'm doing a class and I'm trying to show, something specific, and I sometimes add wood grain or colors, but it's
Okay.
fine. Is it important? No.
Is it a good way to come up with a design for your rocket?
Uh,
Like a color scheme kind of?
no, it's not. It's just
Okay.
bling. Yeah,
Okay.
it just gives you a 3D finished look. So this is paper and this, but I could define this part is red and this part is blue, and so it's not really there's no scientific reason to do it. It just looks cool. Which is nothing wrong with that. Let's just say you're going for fundraising and you want to show an example of your rocket. Tell me this isn't like a cool looking thing, right?
Yeah, that does look cool.
And I actually like this view. 3D figure is kind of cool because you can see inside the rocket and see all the pieces.
Like we found a sponsor and they'll probably like to look at this.
Yeah, this will be very helpful for getting support. Okay, I did forget the bulkhead. So up on our transition up here, we're going to add a bulkhead, and I'll skip that. We'll let it do the automatic. I'm going to make it 3 millimeters thick. I'm going to say from the bottom of the parent part, and if you can see, it's showing up right in the middle of this here, and it should be down here. So I need to slide that down to there. That's where I want my bulkhead, right at the bottom of this coupler. So when the gases, you can't see right now, but when the gases push out, it'll separate here.
Okay.
So everything from that bulkhead up will eject, and your shot cord will be tied to that. Okay, and it's going to be actually made.
Do you really need a bulkhead right here then?
Yes, have to have a bulkhead. You can choose to put it up here or down here. It's much easier down here because you can tie things to it much more easily and stuff. Okay, it says it's 10 grams. I think that's legit. Okay, so our rocket now, you can see, is starting to get a little closer. We have a stability of 2.6, but 2.16 doesn't have any engines in it, doesn't have any payloads in it. So again, we're getting closer. I'm going to go up to the nose cone, and I'm going to create something to hold my altimeter up there. So the altimeter that we're going to use is the Jolly Logic, right?
Yeah.
So let's see here. If we go and search for Jolly Logic, that's the guy right there. And this thing weighs 10.2 grams, but you can't just shove it in there. You get to have something holding it in place, right? So up in here, I'm going to go in and add, let's see, a mass component. I could add mass component. What kind of mass component? It's going to be an altimeter. And it was 10.2 grams, but I'm going to go ahead and I can keep adding, like I can add a separate part and call that my mount for it. But let's just go ahead and make it 25 grams because I'm going to make something to hold it. It can be made out of foam, paper, plastic. You could 3D print, but we need something to hold that sucker in there. Okay, and this is our Jolly Logic altimeter. Okay, and we are going to say, I'm gonna say everything from the bottom of the part component. And right now it has it riding on the nose cone up there. So I'm gonna say, nah, it's probably like here. And I'm gonna make holes in my nose cone to allow for equalization of pressure. So you have to have 3 or 4 equally spaced holes that are identical, and they're probably about 1/4 inch holes, like little tiny holes with a drill bit. And that allows the air flow to go in and out, and that gives you the ability to read. So I'm going to say 10 point, was it 3 grams?
Yeah, somewhere around there.
Add some more for a foam mount. Okay. Now in here in the middle, we're going to do our egg. Okay, so I'm going to click on that part of the tube. I'm going to add a mass object. Call this Humpty Dumpty. Now it should weigh 60 grams, right? And so I could just say 60 grams, and that's Humpty Dumpty. And from the bottom of the component, and I'll put a Humpty Dumpty right in the middle. Just, well, this is actually all payload down here too. All this space exists down there. And I assume we are going to tape the nose cone on so that we'll pop it out there and pull the egg out here. So we do have to figure out, we could fill that space with something, just some foam, however you want to do it. But let's put the egg right in the middle here for now. Okay, let's go ahead and also add another, let's see, this is actually, I'm going to call this one the payload bay. We're going to add another mass object, and this is going to be our egg holder. So in Apogee components, you can find a variety of foam egg holders, egg foam, and they have protectors. So here is a single egg foam for a 2.6 horizontal, that's sideways. So is that what we want? 2 point, is that too big for us?
Yes.
We don't want a horizontal, we have to hold it, we have to hold our egg vertical. I think this is for a BT80, right? Outer to 63. So we're talking about 65 millimeter. Yeah, so this is the wrong size, but this is the basic idea. You can shop around so you can find one that holds it vertical. So I don't want to waste your time. But it's cheap. It's a rock solid thing. You put some like string around it so you push it in easy, but you can pull it out with the string. And
Wait,
this
can we 3D print something like that?
Yeah, but you don't want to 3D print something that's gonna softly hold your egg.
Okay. What if it was like a tight fit on the egg?
You want to make it out of foam.
Okay.
So just find some foam that someone packed anything in, that not styrofoam, but like softer foam that someone got when they got a new computer or a new whatever TV. Find some of that foam and carve it out, and you can cut it, or buy one of these things. So, but it says it weighs 23 grams. So I'm gonna say this is the egg holder, and this is part of your payload. And it was, I'm going to add a little taper string to it, so it's 25 grams. Where it's located from the bottom of the part. Okay, and we're going to put it basically with our egg here. And I can make it bigger, so it kind of looks cool. So it's holding my egg. I get, that looks neat, doesn't it?
Yeah.
But I defined its mass already. So now I have an egg, and I have an egg holder. I have an altimeter, and you can see my center of gravity is climbing up here. That's fine because we're not done. I'm going to click on the booster tube, and we're going to add a parachute this time. Okay, and I am going to buy a parachute. You can make your own. Barbie Pill makes your own, but I'm going to go for diameter. I'm going to start by diameter, and we're in millimeters. Okay. Alexa, how many millimeters is 18 inches? 157. So this is an 18, oh, here it is. It says right here, 18-inch parachute. So here is an 18-inch nylon conical parachute. And here, LSC Precision is one that I've used before. And I know I can buy one of those. So I'm going to choose the LP18. This one is a nylon chute, 8 lines. It has a mass already figured out for you. It knows the material. It knows that it's going to deploy when the ejection charge goes relative to the bottom of the component, just because I'm being consistent. So I know how my part moves around. And it shows that I think in the middle of my transition part right now. So I need to slide that sucker down. Okay, and just for giggles, I can change the way it looks. Yours looked kind of funny.
Yeah, I wasn't sure on how to, because I didn't have like the size or anything.
Yeah, so it's going to be packed up to the top here. Okay, it's going to be packed. So we're going to have recovery wadding or dog barf down here close to the engine, protecting our parachute, and then we're going to have our parachute here. But when it's packed, it's going to probably take up, a little bit of space. So it's going to look like that, approximately. Okay, and that's fine by me. We are going to go in our booster and we're going to add some, let's see, just general mass component. We're going to call this our dog barf. This is an insulation that you can buy. You can buy a giant bag of it. I recommend you buy one bag. It's like $20 and you'll have recovery wadding for the next 10 years.
Perfect.
Okay. And
So it's actually called dog barf.
No, it's recycled newspaper, fire retardant insulation that you can buy at Lowe's or Home Depot.
Perfect.
Okay, and I'm going to use the bottom of the component, and I'm gonna slide that stuff down in here, and just for fun, I'm just gonna make it look. I'm gonna fill the space up. This is just visual, but it's taking up this much space. I'm gonna put a lot of it down there.
Right. We don't want our parachute burning up.
Yeah, and 15 grams, that's probably a lot. I mean, that may be, I may be overestimating that. I mean, maybe it's only 10 grams of it. Okay, now we're getting closer. Okay, we have a rocket. We're missing a shock cord. You did put a shock cord on yours. Congratulations. Okay, so I'm gonna put a shock cord in. I'm not gonna use elastic. I'm gonna use Kevlar. I'm not sure which thickness it is, but let's go with the 12 strand stuff. Now the length in theory should be 3 times the length of your body tube. So our body tube was 400 millimeters. So we would want, quite a bit. Let's say 1,000. We want a long shock cord. The longer the shock cord, the less likely you are to wreck your rocket. Okay, and relative to the bottom, I want to slide that thing down. There's some shock cord, and it's kind of centered between the bulkhead and our engine mount. We're going to actually attach it to the engine mount when I manufacture it, when we build the rocket. Okay, and it says it weighs 208 grams. Well, that is totally wrong. It can't weigh 208 grams. An egg weighs 60 grams. This little bit of string, it probably weighs like 3 grams. So I don't know why it's saying that it's going to weigh that much. There's something wrong with this. And this is why you have to always don't trust, verify. I'm going to override the mass. Okay. And so the mass, this is like, I don't know, 3 grams. We'll say 5, but I really don't think it's very much at all. It definitely is not 200 grams.
Yeah.
Okay, that would often people launch a rocket and it doesn't take off. It doesn't work. And I spend all my time clicking on every part and reading the mass until I find the part where they said their body tube was solid paper. In other words, it wasn't hollow. It wasn't like a 1 millimeter thick wall. It was literally a solid chunk of paper, it was like basically like a wood, like a log. And I'm like, yeah, no, that's the problem. So we have a shock cord. We're getting really close now. Man, I can almost taste it. So we're going to now go to motors and configuration. We have 3 tubes that could accept an engine. Only one of them is my 29mm engine mount, though. So that's the one I'm going to choose. I click on it here. Click on it. Is that where I click on it? New configuration. We're going to use a motor. Hide motors which are not in production. Okay, I'm going to have to get rid of that. Okay, we're not selecting from here. We're going to end up probably using not even SDs. We're going to use Aerotech. So there it is, Aerotech. Okay, so we're going to use Aerotech, and we can sort by diameter, which is what they're sorted. So we're looking for 29mm. Here's where they start. Here's an E, here's an E, here's an F. I have a whole bunch of F20s. It's a cheap engine. It's available. You can buy it. That right now is the name of the game because there's so few engines available. I also have some F50s, but
I
let's
think that
put the
I think
F20.
the F20 is what I put in our.
I didn't see your engine. That was another thing. For whatever, when you saved it, you did not save your simulations, so I didn't get any of that information. So an F20-4 is a great engine. Okay, it's available. It's nice for us. So we're going to choose that. Okay. So I chose an F20-4 in my configuration. I'm going to go flight simulations now. And we're going to wrap this up pretty quick. I'm 10 minutes over where I wanted to be. I'm going to edit the simulation. And in the simulation, I need to start putting some real data in here. I'm launching in Fairmont, right?
Right.
Well, where's Fairmont? So I've already had this pulled up, but I'll just do it again anyhow. So the latitude and longitude of Fairmont is 39.4851 degrees north of the equator. And our longitude is 80.1426 west, or -80 if we're not using east and west. And actually, this has the information from my previous. I said this earlier. The altitude at our actual launch site is like 954. So I said 1,000. But we're not at 0. The default settings that come in here are not right. So my point is, you can get this as accurate as you want. We can also go and say, what is the wind, Fairmont, West Virginia. So I could find out. Right now we have. Whoa, wow! We should go launch right now. Oh, it's dark. It's black. It's dark. It would not good with 0. But it's very common to have, like, 5 to 10 mile an hour winds. If you hit 20, you cannot launch. But here's a wind forecast, and you can get an idea of what kind of winds you're looking at. But so here's direction and strength of the winds. So I can't see 11 mile an hour winds, 4, 3, 2. So you can see that upcoming, we have some pretty strong winds coming up. But what I'm getting at is, in the simulation, I threw 10 mile an hour winds in here. We could say there's 7 mile an hour winds, whatever you want to do, but you should be getting the weather. This is the Fairmont. Actually, it's the no, I'll just call it the Fairmont. I want to call it that. Okay, simulate and plot, and we'll show you in a really cool plot different lines here. Blue is altitude, so it looks like 500.
Only 400 feet.
Yeah. So anyway, so you can see different aspects of it. And how long was our flight? It looks like we hit the ground in 22 seconds.
So it needs to be longer.
Yeah. So here's where we're at right here with this rocket, is that it's saying that it's not quite up there. So I think there's some errors in our design, but what we can do is we can definitely tweak this thing. I do think that the 3D printer transition is not 300 grams. I
Yeah.
don't, anyway, it's 300 grams. I think that we're gonna have to override the mass. And we're gonna say that this thing is, I don't think it weighs any more than the egg weighs. I think
Yeah,
it's
that's
probably less. I'm gonna
really
call it
50.
50 grams. Okay, that's gonna change our center of gravity and the amount of mass in our rocket. Okay. Also our fins, and our rocket's much bigger than it has to be, right? It's
Right.
930 and it has to be 650.
What's a recommended height for, or like length of rocket?
There's no recommended length.
Okay.
My son, when he was like 7 years old, said, I want to build a rocket as tall as my dad. And I'm a whole 5 foot 5 inches. So, but we built a rocket actually taller than his dad. But let's go ahead into our payload bay and let's shrink that sucker down a little bit. It's because this entire bulkhead, I'm sorry, this entire bulkhead slash transition piece is all hollow. So we have
Right.
all this space to store our egg. So let's go ahead and slide this thing down. As long as it was what, it had to be what, 160?
6 inches. So yeah, you're about there.
So let's just say 6 inches. And in millimeters, that comes out to 152. So I made that small, but don't worry, we'll fix this. We'll fix everything else in here. We're gonna go ahead and take Humpty Dumpty, and we're going to put Humpty Dumpty. Let's just consider that again, everything in this whole transition is hollow, right?
Right.
So we're gonna center Humpty Dumpty in the middle of the transition and between the top of the nose cone. Okay, I know Humpty Dumpty's weight is correct. And the egg holder, we'll just put that around our egg. So now it actually looks cool now. Do a quick save. I was going to gratify myself by looking at it in 3D. Yeah, it looks cool. Let's run the simulation again. So I go to simulations. I click on the simulation if it's not clicked, and I run it. We've now had 860. And I think the problem really was that one part was just whacked out. It was just it was inaccurately masked for some reason. I think I may have an error in it. Like I can go back and look if I chose something with solid or something. I'm not quite sure. It's very common to make a typo. But I now have a rocket that's legit. Okay. It's got all the parts I need in it, and it is flying to approximately the right height. I can easily, with a slightly more wind, it's not going to go as high because it's going to spend more time flying diagonal. When a wind hits your rocket, it flies diagonal. Now let's look at our stability, 1.38. Do you remember from our prior lecture what I said would be a ideal stability?
Between 1 and 2.
Wow, pretty good, huh? It's almost like I made this before. So I have a lot of strategies for slowing your rocket down. How was the flight duration now? 42 seconds. Oh my gosh, this is a perfect rocket.
Actually, I think I have it pulled up so I can look.
Okay, so we're there. Do you have, okay, now I know you had some other questions. And I was gonna potentially do a 3D printing, but I think we should probably break that up to another class.
Duration. It was only 27 seconds.
Yours or mine?
Mine was.
Yeah, well, yours had a few technical flaws in the design of it, which hopefully I've eliminated right now. Some of the parts that you might be able to build a little more accurately. Let's go ahead and add an F50 in because I know I've seen those for sale. Okay, F50 with a 4-second ejection delay. So here's a second configuration. And we'll go to flight simulations, F50. Let's go ahead and run that sucker. And we went 1,000 feet. Oop, that's too bad. But it's good to see some different engines in here. By the way, look at the velocity of deployment. 23 is a little too fast. Okay, optimum delay will be 5 seconds. So what that means is we are ejecting our parachute on our way up. Unfortunately, with an Aerotech engine, I can only, try to buy one that's appropriate. I can't, adjust it. So
Right.
we really don't want an F50. But what I end up doing is I end up going to stores and seeing what I can buy. So if I look in here and I say, let's go shop, we're gonna try and buy some rocket motors. We're gonna buy single-use Aerotechs, 18, 29 millimeter motors right here. So here's an F10-4. A long burn motor for small light rockets, not us. F10, no E. And now we don't, I think we want to stick in the Fs. I don't think we want to go in E's. I would stay away from the kits. Aerotech kits are confusing to me. And they require more hazmat shipping. Here's an E24. Nah, let's see. E. Here's an F15. Here's the F24-W, F24-7. I don't think we want to use a 7 because we would be pulling our parachute out on our way back down again. Here's an F23, FJ-4. So let's go under our motors configurations. We'll add a new configuration. We'll add an Aerotech F23, 23. Okay, with a 4-second ejection delay. So you can see if it's a different engine, you just choose the ejection delay up here. Okay, go to flight simulations. Let's run that one. 868. So you can see I'm getting some ideas of how these different configurations are going to work for us. If I want to make it go a little bit lower, it'd be really easy. All I do is go into our fins, for example. So I have some trapezoidal fins, and I just make them a little bit longer. When I do that, let's see here. If we look from the back, this is hard to see. So that they look pretty long now, don't they? I'm not sure how high they were before. So we'll call them 65. They're big fins. No, they don't look disproportionately large. Okay, and we go to flight simulations. Now they're all red because they need to be run again. So run the simulations. And wow, did I get worse? It's higher.
No, it got a little bit better.
Anyway, we can easily add mass to it. So I would add mass in a way that does not wreck our relationship between center of gravity and center of pressure. And so I might go into rocket design, and I typically go and I add some mass in the bottom of my booster area. That's a nice place to add some mass. So like down in here. And so I can just say transition, mass object, some clay, and let's add, I don't know, 30 grams of clay. Where? From the bottom of the part. And I'm going to, I find this addictive, by the way. I get totally addicted to playing with this, and all I want to do is just keep doing that. I'm going to spread that clay out. It's not going to be very long, though. It's pretty thin. Just a bunch of clay down there. Okay, and I give it 30 grams. Okay, good. Flight simulations, regular simulations. So now we're 808 feet. My concern, though, is how long till I'm coming back down. Flight time 38 seconds. I'm not wildly off. I can increase the size of my parachute or something like that. So these are ways for you to play with it. Change parachutes out. But you now have, essentially a rocket with a 1.4 stability constant. It's got all the parts you need in it, and this would be a good model for you to move forward.
Okay.
Any questions?
No, I don't think so.
All right.
So you were saying on Onshape, to make a nose cone, you just got to use the revolve.
Yeah. So why don't I go ahead? I'm going to stop this recording.